completing a square is just stumbling too many people. With that being said, starting off my video, we went ahead and completed the square on this circle before we did ellipses. We filled in these blanks by whatever half the middle term and squaring it on a circle. And this is what we did on Tuesday before break. And then the whole point of taking half the middle term and squaring it, focusing on this. This is the factored form of this now that I created that perfect number there. And then there's your attributes of a circle. And by the way, this is why we're doing ellipses next. Very, very, very similar. How an ellipse looks to a circle. An ellipse is just an oval. A circle is, a nice perfect round shape. So there's a very minor difference in the equation. So, and this is why I said do not print this page. You'd kill your ink. But every year I want to give, props to the book, but also, explain where this stuff comes from instead of just going right into the math. Conic sections are all over in the world. They're in architecture, they're in engineering, they're in astrophysics. The ability to get to Mars. Our orbits are elliptical over time. So we don't just, hey, I want to go to Mars. It's not like going to Orland where you just go straight to Orland using some streets. The stuff's moving out there. We got to figure out how it's moving and where it's going to be at a certain time, based off of that elliptical orbit that can be written as an equation. Blah 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 blah. So this is why we're doing ellipses first, even though it's section A2 in the book. They're almost like circles. The equation is almost spot on. But there's just one minor difference. And then there's a couple other things that you have to be aware of. Hey, there's architecture. Ooh, that's in the news right now, the presidency and, the office changing right now. But anyway, that building has a bunch of conic sections in there. So this is why I said don't write this down, because this is just, I don't want to just go right into the math and say, here's, what we have here. But take this line and rotate it like this about this point, and you create these cones. And then you take cuts out of those cones, which are conic sections. This is why the whole chapter is called conic sections. So the book does an awesome job of denoting this. I just want to make sure you understand why we're using that term. If I take a section at an angle of one of the cones, then this is an ellipse. By the way, if I take a section straight across, then that is a circle. That's why we did circles before break, because actually a circle can be a conic section as well. And that's why it's very related to an ellipse. If I only cut through the top of one of the cones, that's a parabola. If I take one cut right through both cones, this is not a parabola. This is actually called a hyperbola. And that's going to be on, so what do we got here? We got Tuesday today. This is Friday this week. And then this is Tuesday next week. Yay, I lost my pen for no reason. There we go. So that's how we're going to take the days down. We're just going to give you the highlights of each one of these. All right. Are you laughing at me, Aiden? Or are you watching Netflix, a comedy? What's going on? Oh, toe. Gotcha. All right. I'll change that for you, Chief. Tuesday. All right, there we go. All right. Oh, great. This is why I told you not to. You feel free to read this, but here's what would have happened in class. I actually would have done this demonstration, and then I think you guys can still see me. I would have done it on one of those two boards over there. Oh, what happened there? Okay, and I would have. And actually, I ruined a pair of shorts of mine years back because I wanted the strings for those shorts. They were kind of old anyway. I remember them too. Kind of miss those shorts. But anyway, sorry. Um, what I did with the string was I put two tacks just like this, and I actually did two demonstrations of this. One time the string was almost stretched out all the way, so it only kind of tethered like that. So the tack was really spread out, the tacks. And then I took and I tethered that string so it was very tight. And then that's when I dropped the pencil down. and I let the string dictate my actually marker, but that's fine. And I could only do the first half. Then I'd let go of the thing and let the string fall down, and I'd come down here and tether the string. And of course, it would connect here and connect there. And the point of doing this is it's the string that makes the ellipse through this action with the pen and the tacks. And that's kind of setting up the point of why we need to learn what we need to learn coming up here. The string actually is something very specific. Okay, you don't have to write any of this down. I want this in your head so that you understand a couple other concepts that we say later. Oh, and then by the way, I did another demonstration where I put the tack really close together and the string was like really kind of looped like this. And then when I tethered it and made it like this, the ellipse became much more circular. So notice when the string was really kind of low and like very almost stretched out all the way, you got a very elliptical scenario. When the tacks were very close together with the string being very long here, it became more circular. And hopefully you could visualize that. I would actually do it on both of those boards, both examples, and leave them the whole chapter and then reference those two pictures up in the corner over there. But we lose that, with our little e-learning situation. I think it's really cool, but and really denotes something. Oh, and then by the way, um, Earth's orbit is not circular. It's almost circular, but it is actually elliptical. So what's the string? I mean, is there really a string attached to Earth? No. Someone put in the chat, what do you think the string actually is? What natural phenomenon actually acts as the string that makes Earth's orbit around the sun be elliptical? Nobody's going to put it. I was hoping someone cared about astrophysics and watched space shows and took a science class. And thanks, Alexander. I said put it in the chat, but he actually said it. Nice. That works. You're correct. As a Fact, you'd have to ask an astrophysicist. But I don't know, Alexander, if you know that actually stars wobble. And actually, in a star's wobble, that's how we first found out that there were planets in other solar systems. I think that was one of the first methods. But with the sun wobbling, actually, the sun is. Oh, I'm actually ahead of myself. It's the tack. It actually is the tack. It's actually what's called the focus of our movement. So that's how scientists can actually first start finding planets in other solar systems. I firmly believe that was one of the first ways by analyzing another star's wobble. If the star's wobbling, that means planets are going around it to make it wobble. So first evidence that there were planets, and that was only relatively new that we found evidence of other planets. It was in the 1990s. I know you were born after that, but that was in my lifetime where they first found evidence of other planets in other solar systems. So, and now it's just exponentially taken off the whole idea of finding planets. And I firmly believe very, 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 very soon we're going to have a high, strong evidence of intelligent life in other places. It's inevitable. So here's what's true. That's the string. This red that I have here, that's the string. Well, the string never changes its distance. I mean, the string is as long as it is given, so the string that I put up on the board, its length never changes. And when I tether it and I try to draw this ellipse, the distance to those two foci never change. So this is what's true. No matter what point you're at on the focus, no matter what point you're on the ellipse, the sum of the distance to the two foci is constant. So that's a truthful situation. Sorry, so I just threw the word focus out there. Those are called the foci or foci, two focuses. You don't say focuses, you say foci. All right, so did you have to write any of that down? No. I think it's interesting though, and where it has applications. I love science shows. I've been very intense in watching science shows over the years. I think kind of because of teaching math and seeing sections like this, and then hearing some things on science shows, and then making connections there. Okay, so before I go into this, just remember ideas about a circle. Okay, before I get into an ellipse. I don't know why I'm green. Hey, green and red, just in time for Christmas. X squared plus y squared equals r squared. And I had that written down there, so it just reminded me. And then, of course, if the center is h comma k, then it's just x minus h squared plus y minus k squared equals r squared, where now the center is some other number other than 0 comma 0. Hey, just imagine if I did this. I do this every year, and I think those that are really in tune with what's going on in here really can uh, be helped here on how easy an ellipse is. If I just decided to divide both sides by r squared, I think everyone should understand then this equation would just change to x squared over r squared plus y squared over r squared equals 1. And then same thing with this. So just have a leap of faith for a moment. All we did was a simple thing, dividing both sides by r squared so that we get this equal to 1. And then we can compare this to the equation of an ellipse and how it's different. Notice the r squareds are both underneath the x squared and the y squared. And of course, if this is a circle, those numbers would be identical. Here, I'm going to tell you the difference with an ellipse. With an ellipse, the radii value underneath the x squared and the y squared will be different, not the same. So then very simple, if you look at my face, the x-axis radius will be different than the y-axis radius, and therefore instead of a circle, you'll have an oval. Very simple, and actually how to graph this. And then there's some parts after that, like, okay, he identified that foci are important because it's really the foci that draw the ellipse. Okay, so we're going to have to find foci, and where are they located? That's a formula you'll have to have memorized. And that's really about it. The rest of it is terms, vocab, and you should be fine with that vocab as you do your homework. Do you? All right, anyway, here is the difference. And I know I wanted to give the book props, but it does kind of look a little cattywampus right now. And I just want you to focus on a couple things. Focus? He just said focus. Just look at the difference in the equations. This one denotes, well, they both denote that the numbers underneath x squared and y squared are different. And by the way, we're starting with the center being at 0, 0 for this little chart of what I need to know for an ellipse. That's it. You actually, this should be enough to show the difference between a circle and an ellipse right away. The radii underneath the x and the y are different, not the same. All right, so here's what they note, though, and I really don't want you to overdo this. What's A? What's B? It's really not about A and B. Okay, it's really about where is the bigger number. But what they're noting is, hey, if the bigger number is underneath x squared, that means you have a bigger x-axis radius compared to a smaller y-axis radius. So when I draw the x-axis radius and y-axis radius, I get an oval, not a circle, because I have different radii. If the bigger number is underneath y squared, then I have a bigger y-axis radius and a smaller x-axis radius. And I got real obnoxious with drawing ovals here to try to really denote those differences. So in these pictures, if this was really with numbers, the numbers would be greatly different. All right. And then therefore you get a huge ovular scenario. That's actually called something which we'll define later. All right, now I'll let you look at the rest. And you know what? If you printed the notes, great. That is actually a good idea. But all of this is we'll talk about how to get the foci. I crossed this off on purpose because this is robotic formula. I want you to be a grade schooler. I want you to go to a coordinate plane and count to find the foci. All right. And then the vertices. Boy, I'll tell you what the vertices are. There's a major axis. By the way, the major axis is the longer axis. So in this example up here that I'll highlight in blue so you know what I'm talking about, the major axis is left, right. So it is the A value left and right. The minor axis is the B value up and down because that's the smaller of the two radii. And this one, it gets flipped. The major axis is up down because it's the longer of the two radii. And then the minor axis is left right. And these are all terms. I don't think that one's going to be hard to remember. Semi-major, semi means half. It's not really a big deal. So really what's important is the difference in the equation, what they create, the idea of x-axis and y-axis radius, and then our foci equation. And that's a formula. So I'm going to go back down to this, and I'm not going to derive this. You're just going to have to memorize it. The foci are what draw the situation. I don't know why I held up a 2 there. So you're going to have that memorized. And actually, let's think about it. A is the bigger of the two radii. So a squared minus b squared makes c squared smaller than a squared. So imagine I go a right and left. The foci must be smaller because the foci must be inside the ellipse, just like the sun is inside Earth's orbit, and the sun acts as the foci. If you accidentally change this formula to plus, then you say the sun is here and Earth's orbit is here, and the sun is outside of Earth's orbit. How could a foci be outside of the ellipse? So what I'm trying to do is get you to make common sense about that formula and not flip a coin and say, is it plus or minus on the a squared minus b squared? And it's minus. So it ensures that the foci are inside the ellipse, all right? Just like the demonstration with the tax, or at least the talking about the demonstration. I'm going to exercise all the rest of these terms. Semi-major axis, endpoints of the major axis, endpoints of the minor axis, what vertices are. I don't like the term vertices in this. I really think they should cancel that, but that's just me. Okay, so hold off for a second. I know it kind of looks, I've cut it up over the years and, highlighted certain things. I scratched these off on purpose because we're actually going to go to just graphing it and then naming the points and just knowing what a coordinate plane is. If you don't know what a coordinate plane is and how to move on it, I can't help you. That's grade school. All right. That's what we're trying to do, is reduce this to easy stuff. All right. Who did I get somebody already? Oh yeah. Okay, we got him. 4. Are they here? Brianna. Oh, Brianna, dang it. Your 2 N's always make me want to say Brianna. My daughter, I say this all the time, I know. My daughter has 1 N, and that's Brianna, always. But everyone always calls her Brianna. I'm like, Brianna, you there? Yeah, okay. Okay, first things first. Let's focus on this, but we are going to find the vertices and foci. Notice I said let's focus on this. You probably don't know this, but this has to equal 1. So what am I going to do to both sides, Brianna? How do I get this equal to 1? What can I simply do mathematically? Yeah, and if it's not in perfect format, we will have to do this. At the end, Brianna and everyone else, we are going to complete the square, and we'll have to do this little division thing. Okay. For my glorious instruction, Brianna, what is the x-axis radius? Ooh, I highlighted the number. That's important since you went first here. What's the x-axis radius? You are correct. This is how easy it is. What's the y-axis radius? That's why we have an oval. By the way, hopefully you recognized, we go green here, there are no numbers with x squared and y squared. Just like in a circle, that means the center is 0, 0. So the center is the starting, point. And if I were to sketch this, and I actually highly recommend everyone, so you could turn your mic off now. I think you did, but just making sure. The center is where I make these moves from. Just like in a circle, the center is not part of the graph, but it helps make the graph happen. So I go from the center and I go 3 right, 3 left, 2 up, and 2 down. I'm trying to make all the spaces equal. Wish I had a coordinate plane here so that would guarantee that. But I hope you see how this is ovular and not circular. It is more wide than it is tall. This is the major axis. I don't know if I said this, but I'll say it now. The foci must be along the major axis. So maybe I'll go back up to the chart and put foci, and they are always on the major axis. They're on the longer of the 2 radii moves. Has to be, and that ensures that the foci are inside the ellipse. So all I have to do is find that C value, and then that is the move to find the foci where they are in relation to this. Also talking about, I know I'm going ahead of myself, but just thinking about where this is in engineering. Engineers need to know where all these pieces are when they're the ellipse is actually. What's really cool? Anyone ever been somewhere where there's an elliptical roof? And then this was in a movie theater once with it was just really cool that they had an elliptical roof. Roof, is that how you say it? It sounds like a dog. Roof. And they had these positions located at the focal point of the elliptical roof. And it was a very big and very long room. And you know what happened when you stood at the focal point and someone else stood at the focal point? When someone whispered and said a word, it was in the optimal position to bank off of the ceiling and hit the other person at the focal point, and that whisper could be heard by that other person. Is that amazing? Anyone ever seen something like that? Anyone been somewhere that something like that happened? It's actually very, very neat. It was very cool. And me being a math teacher, I'm like, that just blew my mind, man. I didn't know that was a thing, actually. All right. So let's find those foci. Oh, whatever. This is overdone. Okay, C squared equals. All right. I lost my pen. Pen. I don't know if my battery's low. I'm not really sure what's going on. Thought I'd get a message if the battery's low. I think it just disconnects every once in a while. This is great for YouTube. I think it just gave it back to me. Nice. 9 minus 4. C squared equals A squared minus B squared, not A minus B. A squared minus B squared. And then we'll square root it. Okay, so square root of 5. Let me type that on the calculator real quick, just to get an idea of where this is on a coordinate plane. 2.2 is good enough. 2.2. But I'll show you how this works. But I am going to move 2.2. 2.2 right, 2.2 left. Good. The foci is inside, or the foci are inside the ellipse. So that holds true with the string demonstration. The x's are where the tacks are. All right, and that's the best I can do on that. So what did I do for that move? I went right, left, root 5, and then up, down 0 because the center. So from the center, I went right, left, root 5. Okay, I didn't do this last hour because I hate this, but usually what they ask sometimes are, what's the endpoints of the major axis? What's the endpoints of the minor axis? The term vertices, hate this, but the term vertices represents the major axis endpoints. So it's plus minus 3 comma 0 because it went 3 right, 3 left. The endpoints of the minor axis, fine, I'm going to write it down here. Endpoints, minor axis. I'm just going to not write axis. 0 comma plus or minus 2, just to denote some things that they ask you, okay? To actually, but if you just graph it, it's so simple. It really is. All right. I'll let that sink in for a little bit. Some of this is, yeah, a little too much writing there. So it didn't ask me to graph. I still graph and then just look at the coordinate plane and then answer these questions. because looking at the coordinate plane, it's very easy to find what those coordinates are after I make those moves. Just really trying to simplify this for you. It really should be. If you did your circle homework, that's a big if though sometimes. Yeah, I'm throwing it on thick. I'm getting frustrated with students that don't do their work. Any teacher would. 12. Alex. Or do their homework appropriately. Do you know why this is almost circular, Alex? Oh, and I forgot. I got to go back to each one of these and do another term that talks about how ovular. Hey, Alex, why do you think this is almost circular? I thought I heard the thing go on. Oh, yeah. Look at these numbers. These numbers are very, very what to each other? Starts with the C. Close. If they were both 25s, Alex, you would have a circle because the x-axis radius would be equal to the y-axis radius. You got me? You know what I'm saying? Okay, so the center 0, 0. What is the y-axis radius? That one's a little bit easier than the x-axis radius. What is the 5? What do I got to do to get the x-axis radius, or what is it specifically in exact form? Square of. That's the exact form, but that doesn't help me in graphing. So, like putting it on a coordinate plane. So, square root of 21 I'll do for you is 4.6. Notice how close these are? That means this is almost circular. So, I already did the sketch. 5 wrong, 5 up, 5 down. You can turn off your mic. Right 4.6, left 4.6. This is where the tacks are really close to each other comparatively to the last one. And we're actually going to come up with another mathematical term that describes how circular or how ovular. And I'll go back up to the chart of rules for this in order to denote that. Okay, so we got it sketched. So then we should know, okay, I got to find the foci is really the next important thing. 25 minus 21. Well, this is nice. C squared equals 4, a square root. And I get a nice number of 2. But here's the thing. The major axis now goes up and down. So the foci must be on the major axis. So that's where the tacks are. They're up, down, not right, left. So where are the foci? 0, comma. And this must always be in coordinate form because that tells me that you know where the foci are. If you say the foci are plus minus 2, you're done. I'm going to mark you wrong. Okay, so we got to make sure that we know that. You got to tell the teacher that you know it's on the y-axis or along the y-axis, up-down kind of situation. Okay, comparing the last two, all right, there's not a major difference, but there is a difference. I think you understand that this one's more circular than the first example. That is called eccentricity. And I'm going to go ahead and put it back up here in the chart, find a spot for this. Eccentricity may be the first time I've said that word with you guys. All eccentricity is denoted by the letter E. And if E is closer to 1, then this is more elliptical, more ovular. So I'll write that a little bit differently so it's a little bit shorter than I wrote last hour. Elliptical. If E is closer to 0, heck, if E is 0, it is a circle. That's because the x-axis radius and y-axis radius would be equal. So when you took a squared minus b squared, you'd get 0. All right, and then that's why this would be more circular. Now, I didn't even write what the formula is. It's very simple. E equals C divided by the major axis radius, A. So again, like I said, if it was a circle, the x-axis radius and y-axis radius would be the same. And when you take a squared minus b squared, you'd get 0. So that's why if you get an eccentricity of 0, you actually have a circle. You don't even have an ellipse. So that kind of proves that point as well. So why do we find eccentricity? to describe how ovular the situation is. But you don't have to describe it. I'm just going to make you find it. So on the last one, E, let's kind of make a dotted line here. E equals C root 5 over A, which is the major axis, 3. Now I'm going to type that on my calculator just to compare these two. Divided by 3. That's 0.75. Okay. Just comparing these two. Hey, lost the pen again. This is fun. This happened numerous times last hour. I really think it's a glitch. Like this OneNote just kind of stops functioning because it would happen a lot last year in other ways. So we'll just sit here and wait on YouTube. This is the things, technology. Still waiting for the pen to activate. Hit a couple buttons, make it awake. I don't know what that is. That's never come up before. Okay, good. Fun stuff. It's always fun for a teacher when things stop working. I came home a little bit early on Monday, and my wife, her computer couldn't even project her screen. So her lessons were really bad. Okay, this is great. Try this. In and out. Hey, thank you, computer. It's about time. Sorry for yelling in your ear there. I don't even know what I said there. Okay, 0.75. That's great. Took like 3 minutes to get that dang decimal. I almost wanted to swear there. Written down because of this computer. Okay, and then this one, E equals C over A. Okay, that one I don't have to go to the calculator. Did I put 0.6 last hour? Nobody even, I think I put 0.6 here. That's ridiculous. 2 divided by 5 is 0.4. Okay, there you go. You got an eccentricity that's smaller, closer to the 0 side than it is to the 1 side. And we just talked about that one almost being circular. So that's the description of the string. This one, the string, the tacks are closer together. If you took anything out of that beginning stuff, then I'm going to be honest. Now we're going to translate it, and really, this should be all you have to write. And sorry that it's so blurry. Just that when I took a screenshot of it, I don't think I zoomed in enough. And it's because I assume you did your circle homework, and I assume that you understand that now we're going to change the center, and that's the only difference. And now instead of just x squared, it's x minus or plus a number squared. And if you did your circle homework, then you know that the center is h comma k. And then understanding the difference between a circle and an ellipse, those numbers are different underneath. So if you understood that in the last part that I just did, then we should be fine here. Notice I put the circle thing up here. The numbers underneath x squared and y squared are the same. So that's a circle. This is an ellipse. That's the difference. Be careful when the y is listed first. The center of the circle is always h comma k. Remember that, the person that might get picked first in order to answer a question. Okay, and then all the rest of this is repeat and repeat. How do I find the foci? Same thing. Why rewrite that? Don't. All you're doing is this, and then everything is based off of the center, and we'll find all the other information. We're going to keep this simple. I'm getting my student. Come on, who is it? Let's try to get someone not paying attention. Oh, we got an absent person. Did she show up? Ooh, constant absences. I don't know how people survive, man. Missing school. Ryan, you got picked. Sorry, I don't want you to think I'm a liar. 17. Okay, so Ryan, we're going right to an example. Oh, you know what? And foci always on the major axis. We already said that. Don't worry about all that. That's just, I should have cut that out. We're going right here. Okay, so Ryan, we're going to actually graph it too. But tell me, what do you think the center is, after doing your circle homework? What does the center have to be for this ellipse? It's not rocket science. If you did your circle stuff, the ellipse follows along. Okay. If you didn't do your circle, you are putting yourself behind. Ryan, what is the x-axis radius? And actually, this is wrong. This is going to be called B. Doesn't matter, Ryan, don't make a big deal about A and B. But what is the x-axis radius? It's my glorious instructions so far. Okay, so this is the number underneath x squared. What is the x-axis radius? 3. And then what is the y-axis radius? 7. And actually, Ryan and everybody else, before you proceed on and answer any questions about what are the vertices, what are the endpoints of the major or minor axis, vertices are the endpoints of the major axis. You should make a sketch, -2, 1, 2, 3, 4, 5, and make it a grade school question. Everything is based off of the center. My x-axis move, 1, 2, 3. X-axis move, 1, 2, 3. Radius for that. That is part of the ellipse, those 2 points. And then my y-axis radius, you're done, Ryan. 2, 3, 4, 5, 6, 7. Or mathematically, you can add 7 and subtract 7 to the y-coordinate of the center. It's very simple to find those. Either mathematically or graphically, it should not be hard. Oh, no. 1, 2, 3, 4 more. I'm going to try to make this look good. There we go. That's actually the ellipse. Very elliptical. So we can expect this E value to be closer to 1. And that will happen. All right. We'll go ahead and do c squared equals a squared minus b squared. So it's back to the squares so that we know where the foci belong. You do one of two things on this. Square root of 40 is 4 times 10. Square root of 4 is 2. Or 2 root 10 or square root of 40, I'll go back to. That is approximately, so we know how to move, 6.3. Watch what I do with the foci, though. But after I get my next student, if we have time for it. Student number 2, nice. Alexander, who, I think he likes space. Not eccentricity, I just had to get that E. Which way did the foci go? Right, left from the center or up, down? Yeah, because hey, if I went 6 right and left, what do you do? The foci would be out here. That's like saying the sun is here and Earth's orbit goes like this, and the sun is outside of Earth's orbit. All right. So there's another indication of why the foci have to be up and down. Okay, 6 point, that's really actually close to 7 moves. So it's like here and here. This is definitely a case where the string is really stretched out, but the tacks far away from each other. So what are the coordinates of that? There's how you can write it, Alexander and everyone else. -2, 5 plus or minus that C value of 2 root 10. That's the exact format of writing that, because all I did is went to -2, 5, and I went up 2 root 10 and down 2 root 10. So that's not rocket science. That's grade school, just putting it in an exact format. But if you wanted to put it in approximate, -2, add 6.3 to 5, that's 11.3. And subtract. And again, if we don't know how to move around a coordinate plane, that's not me. I can't help you. That's something you got to do. Vertices, that's the endpoint of the major axis. I feel like I lost my pen again. No, I didn't. That's good. Vertices are the endpoints of the major axis. From the center, I went up 7. And from the center, I went down 7. So the vertices are the endpoints of the major axis. I hate that term for this because they're not really vertexes. When we do parabolas, we have a vertex. When we do hyperbolas, we'll have vertexes because we'll have something that looks like 2 parabolas. Okay. Oh, no, actually, I'm doing well. What time? Wait, what did we do? Where are we? I can't get these schedules figured out. All right. And then eccentricity is C over A. So C is that 6.3 value or 2 root 10, over A, which is 7. And then I'll get the approximate to prove that this is close to 1. So 6.32 divided by 7. 0.9. There you go. So there's an eccentricity that's actually really close to 9, and look at how ovular that is. All right. So again, that's why we want to find eccentricity. Okay, that's it for that. And I'll bother a student real quick, but we will get this done a little bit faster now. Okay, who's the students? Oh no. I just like doing it random so that you got to make sure you're paying attention. Abigail Daly. Good. I'm glad to have. Oh, sorry. Don't think I'm a liar. 8. Okay. Abigail, what's the center? Let me see that mic come on, Abigail, so I know you're not sitting there watching Netflix or something. Nice. Hold on. Be careful. Okay. I just want to make sure you relook at that again. What's the center? Be careful. Look at what 1 is with. What letter? What is 1 with? I told you to be careful. All right, and that's a common mistake. I'll tell you what, Abigail, 90% of the time doing these notes, and I do this example, students do what you did, 1 comma negative 2. So that's a learning point. Make sure you're focused on, because if you get the center wrong, everything else is going to be wrong. So I don't want to say I'm glad that happened. Like I'm glad it happened because then everyone else can learn from a mistake, a common mistake, and that's not bad. All right, so we want to put that down, and then real quick, what is the y-axis radius, Abigail? And then x-axis radius? All right, and then from here on out, I'm going to leave students alone because I got to complete the square coming up here too. So, but don't screw it up. And I'm not saying you, Abby. I mean just in general. It's 5 up and down. 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5. All right, and then left 4. 1, 2, 3, 4. Right, 1, 2, 3. I just want to make sure I counted correctly. 1, 2, 3, 4. All right. And then this looks a little less ovular, so I'd expect that eccentricity value closer, well, not closer to 0 per se, but it's not going to be close to 1. All right, 25 minus 16. Ooh, this is nice. Square root of 9 is 3. So the foci are, again, along the major axis. And that is 1, 2, 3 up, 1, 2, 3 down. So the foci are actually -2 comma 3 up from 1, -2 comma 3 down from 1. And you don't want to write that as plus minus 3 because that actually evaluates. This is, you know, and then eccentricity is C, 3 over A, 5. Okay, it's 0.6. So not as big as the last one. That's because this one is not as ovular. All right. I can't believe I think I did put 2 over 5 equals 0.6 last hour. No one said a word. It's kids. And then just some other things as these are the endpoints of the major axis. Which is, I go against this. I don't like this term for this. Vertices. Here and here. And then in green, these are the endpoints. I shouldn't have written here. Endpoints of the minor axis. Sometimes we ask these things as well, here and here. And you have to write those as coordinates. That's a grade schooler. You can, through a coordinate plane, just do the moves in a coordinate plane and find out what those points are. And that's about it. You know, the real big thing is, how do you find the foci? And what's this eccentricity thing? Those are the really only 2 formulas. And then I'm going to be honest, when we get to hyperbolas a week from today, we have foci and eccentricity, and there's just a minor change in the formulas. It's really almost identical how to graph those. All right, here we go. Now I'm going to get crabby and cranky because it is tough when we have so many people that still can't complete the square. and reference. Now we're at the point where we're completing the square, and it's related 100% to that completing the square Halloween worksheet, where only the ones that did it know what I'm talking about. If you don't know what I'm talking about, you didn't do it, and therefore you're severely behind, and you're causing your own destruction. All right, because now we have to complete the square on an elliptical scenario, and it really doesn't take that long. And for those that do know what they're doing and did complete the square successfully, this is going to be easy. All right. So I talk about eccentricity again. I think in the past I didn't talk about it until now. So it's not like this is wrong. I just don't want robot note takers actually rewriting that down. I've already established that. I will talk real quick how I know this is an ellipse. And in the future, hopefully you will know this. Look at your note takers completing the square of the circle at the beginning, and notice that it was 1x squared plus 1y squared. The number in front of the squareds were equal. I know this is an ellipse because the number in front of the squareds are different. Therefore, this will give me different x-axis and y-axis radii. It's all intertwined together. If you've been following me along the structure of these notes, this is why I love math. It's very logical. It's very connected, one piece to the next. That's why the non-homework doers get destroyed, because they don't build their ladder correctly so that we can move on those ladders. Very simple and easy concept. Negative 23 moved over here is positive 23. I make it a big point about that because it makes me sad how many people mess that up. All right, those that are good with completing a square know that that 9 is a problem. You can't have that 9 in front of that x squared. So those that were good with completing a square know what I got to do with that 9. I got to group these two and factor out that 9, and then put a blank for completing the square. This is what I can't help with you anymore. We've talked about this with parabolas a whole bunch of times, but now here is the difference. Okay, fine. I also have to do that with the y squared. It's fine. You could just group them separately and treat them as a separate conundrum. And then you put your blank because now the process has begun. Equals, please don't go this far and be all proud of yourself. And whatever I do to one side, I do to the other is forgotten. Because whatever I put in those blanks, it's got to go on both sides. Oh, but be careful. And don't go anywhere. That bell, if you hear it, means nothing to you. Nobody was here when that bell rang, including myself, because I know our time is a little fast here. Everyone should know what goes in this blank. 1. Half of -2, -1 squared. Everyone should know what goes in this blank. Same number. But here's where it kicks. Hey, put it in the chat real quick. What goes in this blank right here? The answer is not 1. The answer is not 1. Let's see who's first. Who wins? Oh, Michael, you just snuck in, at least on the internet side. I think all of them are pretty close to a tie, though. You are correct. You actually added 9 to both sides, and you actually added 4 to the left side, I meant. So you need to add 4 to the right side. So that's something you got to remember from being skilled with our completing the square with parabolas. And now it's time to do it with ellipses. And we're going to do it with parabolas, and we're going to do it with hyperbolas. All right. We know that we had this very beginning, I think it was Brianna, where we had to divide by 36. And I referenced this, Brianna, when you had to divide by 36 way back when. Yeah, you got to divide by 36 in order to get this into standard form. And then for purposes of the video, I'm going to do one more complete the square after I release you. So 4 over 36 is 1 over 9. Okay, and then this would be simple. Now we see why it's an ellipse. The center is still 1 comma -1, but my x-axis radius is 2, my y-axis radius is 3. I have an oval, not a circle. So I go left, right, 2, up, down, 3. I could find the foci by 9 minus 4. This is almost identical to that one that we had earlier. Square root of 5 is the C value, and so on and so on and so forth. But because of our time, I'm going to let you go. Okay, so you can go there. I'm going to keep videoing myself for that second complete the square, just so there's another example of it, and then compose the video. If you wanted to stick around and see that, that's fine. I know sometimes you do need a break in these days, although there's only one more hour. I do love this day. 8th hour. Silliness. I think it's cool. All right, so I see a lot of people leaving, so I'm going to go to this next one, if not everyone leaving. Okay, I think some people can just go ahead and think of these as grouped already and pull out a 3. So there we are, already skipping steps. Those that are fast and understand this will do that. And then I think you can group these. I don't have time for colors. And pull out a 5. And then that's how 30 becomes 6. Got a better time management 7th hour. I was able to ask students this. Come on, it's plus 42 over here. So this becomes negative 42. Don't make that mistake. All right. Half of negative 4 is 2. 2 squared is 4. Half of 6 is 3. 3 squared is 9. You did not add 4. You added 3 times 4. You did not add 9. You added 5 times 9. So that's the blanks on this side. Can't help you on understanding it anymore. We're beyond and above that. Can't help you anymore on factoring. You've created this perfect factoring scenario. Anyone thinks I'm mean on this, you can only factor so much. And then just at some point, it's got to sink in. And if it hasn't at this point, you got to do something on your own. I am covering it, though. Oh, he's such an ugly, evil, mean teacher. No, I'm not. At some point, got to do the job. It's going to happen in work. You go out to the real world. What's he jabbering about now? 5 divided by 15 is 3. All right. And then just for the purposes of, I didn't do this on the last one, but the center for sure is 2 comma 3 now. Wrong. 2 comma negative 3. Oh, no. You're going to hate this, but the endpoints of the major axis, I'm going to do it in the exact form, and it's actually easier. Since it's my x-axis move, it affects the x-coordinate. And all I did wrong, 5 minus 3 is 2, and then square root it. That's what C is. Oh, no, wrong. I'm doing a foci. I'm a maroon. The radius for the x-axis is root 5. So I go root 5 right and left. Speed kills sometimes. The endpoints of the minor axis are the move for the y radius, which is root 3. That means you go up, down from the center, root 3. Shouldn't be any rocket science here. And then the focus, that's what I was trying to do too quick. 5 minus 3 is 2. And then square root it. And where is the focus? Along the x-axis. So it affects the center x coordinate. And then eccentricity is square root of 2 over, oh boy, square root of 5. If you rationalize that, multiplying both top and bottom would be root 10 over 5. Ooh, that's a nugget of information that no one's going to watch. And then what is the square root of 2 over the square root of 5, or the square root of 10? I'm going to miss my next hour. Divided by 5. 0.63. So, not too ovular. All right, so after we completed the square and got this all, it's pretty fast to find all that information. All right, real good one to do at the end. Again, that nobody's going to see because I don't think anyone's going to watch this.